Section 7.3 is entitled Repeating Decimals, and we're going to go back to something we did in an earlier section and think about that first. The first question I'd like for you to think about is, when did we say that a fraction could be written as a terminating decimal? This is a couple of sections ago. If you'll remember, we talked something about the terminating decimal coming from a fraction that had a certain kind of denominator. In particular, Theorem 7.1 said if the simplified fraction or the reduced fraction let's say reduced fractions denominator contained only factors of 2 and 5. So if you remember, if we had, for instance, a reduced fraction that had a factor in the denominator of a 3, like the number 1/6, for instance, factors into 2 times 3, that 3 being in the denominator would cause it to actually not be a terminating decimal. So, what happens when the fraction can't be written as a terminating decimal? Well, if we have a fraction is or can be written as an integer over an integer, and it doesn't terminate, then it will repeat. So that's where this section is actually coming from. It's sort of the one next step of what we did with decimals in section 7.1. This idea of being able to take something that's not able to be terminating, but then express it in a different way. Okay, so we're going to do an example. Example number 1 says to find the decimal representation for 1/24. So we're going to divide the number 1 by the number 24. And clearly, as it is right now, 24 doesn't actually go into the number 1. So we're going to put in decimal places and put some zeros in here. We're going to need several in the end, so I'm just going to go ahead and put in several right now. Okay, so we're going to move the decimal up to the top. And 24 does not go into 1 or into 10, but it does go into 100. So 24 goes into 100 4 times. 4 times 24 would be 96, which gives us a remainder of 4. And we'll carry our 0 down. So this would be 40. Well, 24 goes into 40 one time. That's 24. Give me a remainder of 16. We'll bring down the next 0, 160. 24 will go into 166 times. And 6 times 24 is 144. And if I subtract, what you'll notice is I get 16. Well, 16 was the remainder I got in this last step as well. So from here on out, every time I do this, I'm going to get 16 that becomes 160, goes in 6 times, I get a 144, and subtract it to get 16. I'm just going to keep repeating that very same process over and over and over again, and that's at that step. So the decimal representation is written as 0.0416. There's a bar on top of the 6. The 6 is what repeats. Be very careful on your bars that I can tell what the bar is actually repeating over, not just randomly over anything. We call this kind of a decimal a repeating decimal. And the repeating block of digits is called the repeat end. This is repeating decimal and repeat end. Note is on here. I expect to see division when you convert these. I know your calculator can convert these with a touch of a few buttons. But again, like we've talked about before, the students who would be learning these kind of activities would not be using calculators to do this. So I want to make sure that you are proficient and comfortable with doing this without a calculator as well. All right, so we're going to do another example. 29 over 99. Okay, so we're going to divide 29 by the value 99. And as with the one before, of course, it doesn't go in, so I'm going to put a decimal point and a 0 and put my decimal point above. All right, so 99 goes into 290, actually, 2 times. And 2 times 99 is 198. So if we subtract 290 minus 198, we get 92. And then we need another 0. Okay, so I have 920. Okay, so 920. Well, 99 goes into 920 9 times. And 9 times 99 is 891. And if I subtract this, I get a 29. Now, the soonest I place, the first time I should say, that I get a repeating value is the first time that I will actually see this repeating process start to happen, and it'll start to tell me what is actually repeating. So if you happen to not notice this, let's say for instance you got to this 29 and you just kept going. Well, what you'd end up doing is you would end up getting a 2 up here. It goes in 2 times, and we'd bring down 198, and we'd subtract, and then we'd do the next one. It would go in 9 times, and you would very quickly start to see that the 2929 is what's repeating. And so my actual answer is that I have 0.29, and the 2 and the 9 repeat, not just the 2 or just the 9. You can put a 0 in front if you like, or you don't have to either way. But this value is actually a repeating decimal 0.29. All right, what we're going to do next is we're going to take a repeating decimal. We've sort of taken fractions and written them as repeating decimals. So now we're going to take a repeating decimal and turn it back into a fraction. This process looks a little bit less familiar probably to most of you. It's not especially complicated, but there are some details that you want to make sure that you understand and process in the right order. All right, so what we see here is we see that we have a value of 61 hundredths, and the 61, both pieces, is repeating. And we're just going to give this the name n. There's nothing special about it, and we're just using it. It's kind of a dummy variable for right now. All right, what you do next is you actually look at how many decimals repeat. So in this case, I have 2 repeating decimals. So what I'm going to do is I'm going to multiply by 10 to the power of 2, because I have the 2 repeating decimals. But if you'll remember, 10 to the power of 2, well, that's just 100. So we're going to multiply both sides by the value 100. Okay, so on the left-hand side, obviously, I end up with 100n. On the right-hand side, this is interesting. So obviously, the 61 that's underneath the bar right now is going to be multiplied by 100 and move in front of the bar, so I have 61. But what you notice, or what you should remember or be aware of, is that when you have this 61 repeating, it looks like this. So if I move the decimal so that I have the 61 in front of the decimal point, I still have the 61 repeating afterward. That did not change. So I end up with 61 and then decimal point 61 repeating. Now, it might feel like, well, what did I do that for? What's next? I mean, it doesn't look sort of like it helped me any. But it actually did. What we're going to do is we're going to come back up here and we're going to recognize that I know a value, namely n, for the 0.61 repeating. Basically, we're going to subtract what's in yellow from the equation that I'm currently working with, that line of the equation. So I'm going to subtract n on the right, and I'm going to subtract the 61 hundredths on the left, because n and 61 hundredths, repeating, are the same. So I'm allowed to do that. I can add and subtract as long as I'm adding and subtracting the same thing on both sides. So this gives me 99n on the left, and it gives me 61 on the right. And you'll notice there's no more repeating decimals, which is a beautiful thing since these subtract out. And then my last step, of course, is to divide by 99. And then if I have the ability to do so, that is, if it's this not in reduced form, I would actually go in and reduce it. This actually is as simplified as this particular one gets. There aren't any common factors. So at that point, we're actually done. This fraction that corresponds to 61 hundredths is the fraction 61 over 99. So let's try another one that looks almost the same, but the only difference is that it's just the one that's repeating now, not the 61, just the one. Okay, the process starts the same. I write down n equals. I write down my decimal point and my 6-1 with my 1 on the line on top of the 1. And at this point, I notice that I only have one repeating decimal. So I'm going to multiply by 10 to the 1, which is 10 on both sides. Okay, so we'll multiply by 10 on both sides. On the left, of course, this becomes 10n. On the right, you'll notice the only thing that moves in front of the decimal place is the 6. And then while I could write 6 point and put the 1 repeating there, it's not exceptionally helpful to do that because I'm going to be comparing it to a 1 in the hundredths place in a moment. So for the sake of what I'm going to do, I'm going to write the 1 repeating where it is. Remember, this really is just the same as this value, right? And it keeps going forever, so dot, 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 something like that. So I can move the decimal point 1, and this would be 6.11111, all these ones. And again, while I could write it 6.1 repeating like this, I could also write it 6.1 repeating like this, and it would be a not so simplified version of it, but at least a more helpful one for the one we're working on right now. All right, so once I get this actually written down, I'm going to subtract n on the left and subtract what n equals on the right. And n in this problem equals 61 with the 1 repeating. And now you'll notice exactly why I wanted the repeating parts to line up. When I subtract, they go away. So on the left, I end up with 9n. On the right, I end up with 5.5. And as with the last problem, we're going to divide by the coefficient of n, in this case the 9. And we're going to take notice of the fact that while 5.5 over 9 is the answer, it's not exactly in the form that it asked me for. It wants me to have integers on top and bottom. So we're going to multiply top and bottom both by 10. That will get rid of the decimal on top, and I have 55 now over 90. And then we're going to notice these are both divisible by 5. We're going to give them a division by a factor of 5. And that leaves me with 11 over 18. And that actually is as reduced and simplified as this particular value will get for us. All right, we're going to do one more of these. The one more of these, however, is probably the most interesting one because of what it is. We're going to do 0.9 repeating. And if I were to ask you which value is bigger, this 0.9 repeating or the value 1, you would probably tell me that the value 1 is larger than the value 0.9 repeating. And we'll come back to that argument at the very end of this problem and ask the same question again. Now the process still to change this into a fraction is the same as before. We're going to put n equal to 0.9 with the 9 repeating. We notice there's only one repeating value, so we'll multiply by 10 to the 1, which is 10 on both sides. Now when I do that, of course, I get 10n on the left. On the right, I get 9 points, and then again, it's 999. All the 9s keep repeating, so 9 repeating. I subtract n on the left, and I subtract what is n equal to on the right. Well, it's equal to 0.9 repeating. On the left, I subtract, I get 9n. On the right, I subtract, I get 9, because these two add to 0. All right, and then if I divide by n, divide by the value in front of n, 9, I actually find out that n equals 1. This value that I originally started with, 0.9 repeating, is simply another way to write the value 1. They're exactly the same amount, which is kind of a little bit weird, I recognize. But it is mathematically correct. Those two are the same thing. All right, using that idea, we're going to do an example that has a 0.9 repeating in it. And it tells us it wants us to find any decimal between the 0.9 repeating and 1.1. Now the easiest thing to recognize is what 0.9 repeating is in terms of another value. That is to say, this is the value 1 and the value 1.1. So finding any decimal between them, the easiest one to find would be maybe the midpoint one, the halfway point. If you'll notice, that's actually the directions on part B to specifically find that halfway point. So let's actually do that down here. We'll find that halfway point up here, or down here in part B. So between 1 and 1.1, we find the halfway point or the midpoint by adding them together and dividing by 2. So this becomes 2.1 divided by 2. And that value is actually 1.05. That would be halfway between 1 and 1.1. And that makes sense if you think about it in terms of money. 1 is like $1. 1.1 would be actually $1 and a dime. Well, what's halfway between? Well, $1.05. Now that we have $1.05 here, there's nothing special about this except that it's specifically a halfway point. Any value in between would work. So we could put in 1.01, like $1.01, or 1.02, or 1.086742, I think 98, I don't know, whatever it is we have. Any of these numbers are actually between 1 and 1.1. All right, last problem for this section. The interesting thought that you probably haven't processed through before in quite this way. Example 7 says the following: sum addition problems are easier to compute with fractions. I know, it's a surprise, right? And some are easier to compute with decimals. Probably not a surprise. But for example, if you had the values 1 over 7 plus 5 over 7, that is much easier to compute than 0.142857 repeating plus 0.714285 repeating. That's not cool at all. But on the flip side, if you had the decimals 0.4 and 0.25, that is easier to compute than if you had 2/5 and 1/4. So our directions here are actually not to discuss whether those are easier or harder above, but it's actually to describe situations where you think it would be easier to work with fractions than decimals and vice versa. So we're sort of, it's like a pro and cons list if you think of it that way. So we're going to write down fractions first and think about when in the world are fractions easier to work with. Now if you compare over on this slide, the 1 over 7 and 5 over 7 to the 2 over 5 and 1 over 4, you might in fact notice that the first set has common denominators and the second one doesn't. So fractions are easier certainly to work with when you have common denominators. Or maybe it's quick or easy to find those denominators. I'll put the common denominator CD. So decimals. When in the world is different about the first decimal than about the second? Again, what you probably noticed on this one is, one thing that you might have noticed is that they're really long. I mean, the first two actually have 6 digits, whereas the 0.4 and the 0.25 have at most 2 digits after the decimal place. That makes it a little bit more complicated. So if we're talking about something that is a long decimal expansion, that's one possibility. But more problematic is actually the fact that the first set is not especially friendly or easy to work with because it's got that repeating bar on the top of it. So if decimals are easier to work with, if decimals are terminating, they're easier to work with. So this is a one possibility down here as well. All right, that's it for section 7.3.